One night to be confused, one night to speed up truth. We had a promise paid for us and then.
Okay, so let's do an example of finding a projection. Okay, so what we're going to do is find projection of the following. Of u, and this is going to be equal to 4, 2, 6, along v, which is going to be the following 3, 1, 7. Okay? So let's go back and we'll find projection of u onto v, which could also be called u parallel. Alright? So our formula, let's recall that. So we have u dotted with the unit vector in the v direction, and then multiplied again times the unit vector in the v direction. So remember that when we do the dot product, that is an operation that takes in two vectors, two vector quantities, and spits out a scalar. So this is going to be a scalar number. And then we also have this other vector over here. So we're ultimately going to get a vector, and it's like a scalar multiple. Okay? Same kind of concept here. Another way to rewrite this, so it makes it a little bit simpler, is we have vector u, and then v on the top, and then this will be over the magnitude of v squared times another v. Okay, so now all we do is basically just plug in the vectors and do what these instructions here say to do. So what we have is, I'll write u parallel. Okay, so projection of u onto v, it's going to be u dot v, so 4, 2, 6, dotted with v, which is 3, 1, 7, over the magnitude of v squared. So we're just going to square all of the components and add them together. And normally, to find the magnitude, we would square root it. But since we're squaring the magnitude, that's just going to go away, and we don't even have to write the square root in. Okay, so this is on the inside in the parentheses, and then we're just going to write the vector v out here. We'll need that at the end. Okay? All right. Now we're just going to compute the dot product on top. So we're going to multiply the corresponding components. So 4 times 3 is 12. We're going to add it to 2 times 1, which is 2. And we're going to add that to 6 times 7, which is 42. Okay, and then on the bottom we're going to have a 9 plus 1 plus 49. Okay, so this is, again, you can see how it's going to turn out to be a number. Everything in the parentheses, and then we have our 3, 1, 7 just sitting out there. Okay, if we continue, what we get is just, on the top we're going to have 14. Let's see, 14 plus 42. So that's going to turn out to be a 56. And this is over 59. Okay? And then we have 3, 1, 7. And if you'd like to, you can factor those, or distribute those in, but I'm just going to leave it here. And this is our projection of u onto v, or along v. Alright, so now we're going to go over one last concept for this video, and it is called decomposition. Decomposition. Okay, and what that means is we're going to take our knowledge of the projection of u onto v. So here's u, here's v, alright? And our projection, again, remember another name for it was u parallel, because the projection finds how much of u is pointing, of u arrow is pointing in the v direction, right? So I'm going to blow this up, and we're kind of going to ignore v for now. So here's vector u. Here is vector u parallel, okay? And this, remember, it was formed by dropping the perpendicular. And now what we're going to do is actually consider what is this perpendicular thing, okay? So I'm actually going to, hold on here, I'm going to move the u so I can label it. There we go. So this is u, the vector. This is u parallel, okay? And this part, we're actually going to name this vector, this one sticking up here, that's called u perpendicular, okay? So as you can see, we kind of just broke it down. We decomposed u, our original vector, into a parallel part, the part that lines up with v, and a perpendicular part, the part that is perpendicular exactly 90 degrees, or pi over 2 radians, away from v, okay? So what we're going the basic concept is the following, that we can make u, or we can break it down into the parallel component and add it to the perpendicular component, Okay, see how just using the properties of vector addition, if you have u parallel and we add on the perpendicular part, u perpendicular, what you get as the resultant vector is our original u vector back, right? So this equation holds true due to vector addition. So again, this is the part that is parallel to vector v, and this is the part that is perpendicular or orthogonal to v, vector v. Okay? So let's do an example of how you could decompose a vector like this. So what we're going to do is decompose the following. We have u arrow equaling 5, comma 1, comma negative 3. And then we're going to decompose it with respect to the vector v equals 4, 4, 2. Okay? So what we want to do is basically to decompose something, we want to get it in a form like this. We just want to be able to write this equation, but with actual like numbers in them. Okay? So the first thing I would do, so we already have our left side. That's just 5, 1, negative 3. We do know how to find the parallel side. That's our projection of u onto v. And to find the last quantity here, all you have to do is subtract the parallel side over here, okay, and see how that turns out to be 0. And to find u perpendicular, all we have to do is take our original vector, subtract the projection off, and we get the perpendicular part is the only part that's left, okay? So that's the process. That's what we're going to do. So we have this part. We're going to find the projection, and then we can find this last one by subtracting those two quantities. All right, so let's find the projection first. So we're going to have u parallel is going to equal u dot v over magnitude of v squared times vector v. Okay, so let me rewrite this here. So we have that equaling, now let's actually plug in our vectors. So we have u being 5, 1, negative 3, dotted with v, which is 4, 4, 2, over its magnitude squared. So that'll just be the sum of the squares of the components of v. And we don't need that square root sign because we're squaring it away. And then lastly, we have our 4, 4, 2 sitting at the end there. Okay. So let's simplify some more. I'll go down here. So u parallel is going to be equal to 5 times 4 is a 20, and then plus a 4 minus a 6, okay? And then that'll be over 16 plus a 16 plus a 4, all right? And then we have our 4, 4, 2. Okay, continuing, on the top we get 20 plus 4, 24 minus 6 is an 18, and that'll be over 32, 36, and this will be 4, 4, 2. So this simplifies to 1 over 2, and then if we simplify that even more, if we distribute that in, we just get the vector 2, 2, 1. Okay? So this is the projection. This is our u parallel, so the projection of u onto v. All right? So this was our second step here. So I'll continue this on the next slide. All right. So now we have u, which equals 5, 1, negative 3. We have u parallel, which equals 2, 2, 1. And now we need to find our third component here, which is u perpendicular. And the way we find that is we subtract u, the vector u, minus the projection of u. Okay? So that'll just be 5, 1, negative 3, minus 2, 2, 1. And that's just going to equal 5 minus 2 is a 3. 1 minus 2, negative 1, and negative 3 minus 1 is a negative 4. Okay, so we found all of them. Now we have our third piece here for our puzzle. Okay, so our decomposition is going to look like the following. We have u, we want u equals u parallel plus u perpendicular, so we just plug those in, and we get 5, 1, negative 3 is equal to 2, 2, 1. Plus 3, negative 1, negative 4. And we can always check to make sure that that's right. So we have 2 plus 3, that's 5. 2 minus 1 is 1. And 1 minus 4 is a negative 3. Okay, so we're good. And now you might be thinking, okay, this is really silly because couldn't I have just picked any vector for this one and then just made another vector so it matches up and equals the left side? No, not necessarily, because what we wanted was that this part had to be parallel. Remember, it has to be parallel to our vector v, right? And our vector v was 4, 4, 2, okay? Which was 4, 4, 2. So as we can see here, our 2, 2, 1, that is parallel to 4, 4, 2 because it is a scalar multiple of it. It's v, 1/2 of v, right? So this is parallel to v, and then this part happens to be, because it adds up with it to make our original vector, this is perpendicular, aka orthogonal, to our vector v. Okay? So these are very particular to the problem. Alright, so that wraps up this video. I hope that helped, and good luck on the homework.